Everyone, welcome to the April by Data Jidda meetup. I'm your host, and working behind the scenes, the by Data Jidda team members, Yasmin, Hassan, Abdullah, Najla, and Rinat. Our talk today is by Michael Alcorn about baller2vec, which is a multi-entity transformer for multi-agent spatiotemporal modeling. Michael is a PhD student in Wayne's Deep Learning Lab at Auburn University, and was also a data scientist and machine learning engineer at Red Hat. He's also a prize winner in the research papers competition at the MIT Sloan Sports Conference. And we are excited and looking forward to this talk. And we also want to thank our sponsors, NumFocus and Moodle. Finally, follow us on Twitter for more details about upcoming meetups to get notified. I think that's all from my side. Over to you, Michael. You can share your screen.
Okay. All right, great. So can everyone see the screen?
Yeah, you can see.
Okay, great. Yeah, so thanks a lot for the invitation. So yeah, this talk is going to be, I guess, kind of technical at times, introducing this new neural network architecture known as transformers and describing how I generalize it to multi-entity data, so multiple individuals at a single time step. And so if at any point anyone has any questions or anything like that, or any comments, feel free to stop me and we can discuss them right then and there. You don't have to wait till the end to bring up a question. And maybe just like let me know if you ask the question so I don't miss it, basically, like if it's in chat or anything like that. But yeah, so if there are any NBA fans in the audience, I want you to take a few seconds and try and predict what's going to happen shortly after this moment, featuring LeBron James, who's trailing behind a ball handler who looks like he's about to go in for a layup. Okay, so let's see what happens. From another angle. And so most basketball fans probably could have told you what was going to happen there because they've seen LeBron James in similar situations a ton of times. And what often ends up happening is LeBron ends up making the block. So today I'm going to be describing our research where we set out to design an artificial intelligence that can learn to understand multi-agent spatiotemporal systems like the game of basketball simply by watching them. And so in the long term, these types of models can be used for counterfactual analysis. So in the context of basketball, that could be to project the impact of trades or predict the outcomes of different play designs. And so like challenges with this type of data is that agents are unordered and interact in complex ways. And so that can lead to interesting design challenges when trying to come up with a learning algorithm. And in addition, because we're working with sequential data, that's going to be very large and cumbersome. And so we need to keep computational efficiency in mind when we're designing our AI. And so the two tasks I'm going to be focusing on today are predicting the trajectories of the ball and predicting the trajectories of the players and predicting the trajectory of the ball. So I want you to keep those in mind as we go through the slides. I'll reiterate them later though, of course. And so what exactly makes multi-agent spatiotemporal data strange? And so to demonstrate that, I want you to consider a simplified trajectory prediction task where we're given the locations of the players on the court at one time step, and all we're trying to do is predict where they will be in the next time step. And so we only ever have one frame of data as input in our model for our training set, and we're only trying to predict where the players will go one step in the future. And so what you see here is just basically the shapes are the players in the current time step, and the errors are where they end up in the next time step. So that's what we're trying to predict. And so one naive strategy to solve this problem is to use, is to use a bag of, well referred to as a bag of players representation. So if you're familiar with bag of words, I'm basically talking about the same thing, just in terms of players, where we have a vector that is n times, it looks like there's some drawing going on the screen.
If there's anyone who doing that, or
Let's see. Okay. So yeah, we're looking at a bag of players representation where the input is basically the number of players times the number of input features per player long, where where n in this case is the number of players in the NBA. So it's gonna be 450, and f is just gonna be 2 because all we're considering is their location on their court, so their coordinates on the court for that input time step. And so what you can see down here is basically like a toy example of that, where anytime Steph Curry is involved in the play, his coordinates would go here. Anytime LeBron James is involved in the play, his coordinates would go here. And so there are several issues with this type of input. The first is that it's extremely data inefficient. And so just a reminder what the standard neural network operator is. We do a linear transformation on the input followed by the addition of a bias vector, and then we pass that through some nonlinearity. And so if we're going to predict 121 different trajectory labels, which is what I did with baller2vec, that would require 450 times 121 times d parameters in the classification layer because of the size of our input, right? Where we have these 450 players. And so d is 512, meaning that's the number of features that are being fed into our final classification layer. And that's not a large number. If you work with neural networks, you know that. So that's what the dimension of the model, internal dimension of the model is in baller2vec. That would lead to 28 million parameters in that only in that final classification layer. And that's more than all of the parameters in baller2vec. In addition, only a fraction of those, only 2.2% of these classifier parameters would be updated per sample because only 10 players are ever involved in a play, right? And so all of the players who aren't involved in that play, their parameters won't get updated. And so it's extremely data inefficient, this bag of players representation. In addition, each lineup is basically a completely different input. And so, for example, how would this type of model, how would this type of representation handle trades? And so you can imagine basically that LeBron, you train your model and LeBron James is on his team. And so the players only ever, the model only ever sees LeBron James with a specific configuration of other players in the lineup, right? And so in that input vector. And so Anthony Davis, another player in the NBA, is in a similar situation where the model during training only ever sees his input features in combination with a subset of other players. And so the model might learn a positive weight for LeBron James that interacts with the other weights of his teammates in the training set, while it learns a negative weight for Anthony Davis that interacts with his other teammates in the training set. But now you can imagine if there's a trade where Anthony Davis and LeBron James are on the same team, that positive and negative weight might end up canceling out or just have unexpected behavior. And so basically this this input representation has unpredictable behavior when you want to alter the lineup. In addition, this input has no way of handling new players. And so you can imagine that you have a way to basically encode a amateur or a draft pick's skills, so someone who's not in the NBA yet. And you would like to be able to use that, right, to make to do predictions and inference with your full NBA data set. And so unfortunately, this model cannot use that information. And so you would have to basically, the only way you can add a new player to this model is you basically have to extend that bag of words vector to have a new slot for this new player and basically gather a bunch of data for that player and then retrain the data set. And so this bag of players representation has several issues. An alternative strategy is to use a vector that is only has the number of slots for the people who are on the court at the time. And so there's 10 players in the court, and so we could have a vector that is 10 times f long, where f again is just going to be 2 because we're just going to, for our simplified task, we're only looking at the player's coordinates. And so the problem with this is, where do you put the features for each player? You can't use the player's position because players often play multiple positions depending on the lineup. And so LeBron James is famous for his ability to play any position on the court. And so you can't just put him in one single slot every time because it doesn't translate to what other players would be going in that same slot essentially. And so we would like to basically find a data set, a data structure that sort of combines both of these aspects, that recognizes the fact that players are different and they have different qualities. And so we want to be able to capture that fact, but also be realize that we don't need to have inputs for every single player in the NBA in our training set. We want to be data efficient. So we only want to be updating the people who are involved in the play at every sample. And so the data structure that we ended up using is basically a sequence of sets of feature vectors, where at each time step, we have a set that contains information about each player's identity and coordinates on the court. And so what you can see here, basically at each time step, we have a set where each circle corresponds to a player's input features at that particular time step. And what those input features are derived from, so this is a feature vector that's 512 dimensions. It's generated by embedding a player's identity. And so this is just like a word embedding, but I'll go into this a little bit more later. So we map the player's identity to a player embedding. You have the player's X coordinate and Y coordinate at that time step. And then this is a contextual vector. In our case, we only use a single binary variable indicating which side of the court the player is attacking to. So the white team in this, or the gray team in this GIF, is going to the left, so they would get a 0. The white team is going to the right, so they would get a 1 there. We then pass that input feature vector through a MLP, multi-layer perceptron, and that maps it to a 512 dimensional vector. We do that for each player at that time step, and then we put them into a set because, again, players are unordered. By collecting these sets over a sequence of time steps, we then have a sequence of sets of feature vectors. And so the two tasks we're going to be investigating again are forecasting the player trajectories. And so basically we have our input sequence of sets, and in this case, we are also going to have an output sequence of sets, where at each time step, we have a label associated with each input player. And this label corresponds to the player's trajectory for that time step. So in which direction they went one step ahead in the future. And we want to learn an F, a function that maps this input sequence of sets to a probability distribution over the output sequence of sets. And we want our F to be causal, meaning that at each time step, we only use information that is available at that time step and before. So we don't want the model looking in the future, because obviously that would be cheating. The other task we're going to be considering is predicting the ball trajectory. And so rather than a sequence of sets as the output, we just have a sequence of individual labels, which is the ball trajectory. So again, in this case, we have the input feature. The input is the positions and identities of the players on the court. And then we also have the position of the location of the ball on the court. I should mention that I also have the location of the ball as an input in the player trajectory forecasting task as well. So we know the players on the court, their identities, their locations, and we also know the ball's location in both cases. And then we're trying to predict the trajectory of the ball here. And so the F that we're going to be using is a multi-entity transformer, baller2vec, which is what we introduced in our paper. But before I get into the details of that model architecture, I want to quickly review a few different deep learning concepts that are relevant to why we went with this multi-entity transformer. And so the motivation for transformers in the first place is because it's a different type of sequential model than a recurrent neural network. So a lot of you are probably familiar with recurrent neural networks already, but just to reiterate how they work, you basically have a sequence of input vectors as your sequence of vectors, feature vectors as your input. And the model works by basically doing a linear transformation of your input at each time step using a weight matrix. This is for the vanilla recurrent neural network. LSTMs and things like that they do more fancy things, but their basic principle is similar. So we do a linear transformation to our input feature vector. So at x1, we do a linear transformation. We then do a linear transformation to a hidden state from the previous time step. And so this at the beginning, this would be an A0, which could be learned or just initialized to zeros. And then we add a bias vector and we pass that through a nonlinearity, and that gives us our hidden state at that time step. So that's what would be here. To get the output, we then do a linear transformation to the hidden state, add a bias vector, and pass that through another nonlinearity, and that's how we get our predictions. For the next time step, we use that input features for x2, do the same linear transformation. So these weights are fixed across time, which is how the recurrent neural network works. We then use that same hidden to hidden layer linear transformation, apply that to the one that we generated in the previous time step, add a bias vector, pass that through nonlinearity, and get our next hidden state. And so that's the basic way these recurrent neural networks work. So some issues with recurrent neural networks is that they can be really slow and cumbersome to train. And so they have these vanishing and exploding gradient issues. And the fact that they're where basically your gradient disappears or it explodes as you go deeper into the network. And because they are inherently sequential by design, you can't process the second time step until you process the first time step. So you basically have to loop through, which can make things really slow because it's not in parallel essentially. Another important concept here is the notion of embeddings. And so a lot of you are probably already familiar with embeddings as well, but just to reiterate what they are, the classic way to represent elements of a set in machine learning models is as these one-hot encodings, where you basically have a vector of zeros that's the size of your set, the number of elements in your set, and you put a 1 in the slot. You put a 1 in a slot to indicate a specific element of your set. So for example, if you had a vocabulary consisting of the words dog, cat, and constitutional, you could develop a corresponding one-hot encodings that are each a vector that is 3 elements long. And then you could have a 1 in the first slot for dog, a 1 in the second slot for cat, and a 1 in the third slot for constitutional. And so the issue with this type of input is that it's basically treating every element as equally similar or close, because like if you take the distance between any of these vectors, it's going to be the exact same. Or if you take the dot product between any of them, it's going to be exactly the same. But we know that these elements of the words have different, some words are more similar than others, and we would like to be able to encode that. So the words dog and cat are semantically more similar than either of them are to constitutional. And so embeddings encode the fact that we think elements in the set share latent features that are relevant to the task. So for basketball, like the players have these latent skills, for example, their 3-point accuracy, their dribbling skills, their athleticism, things like that, essentially, that we'd like to basically be able to exploit for our trajectory forecasting task. And so just as an example, up here are some word embeddings that these are word embeddings I trained when I was an employee at Red Hat. And basically one really interesting aspect of these word embeddings is that you can do algebra with them that corresponds to analogies. And so if you take the word vector for Mozilla Firefox, subtract the word vector for Linux, and then add the word vector for Windows, you get a word vector that's really close to the word vector for Internet Explorer. And so this analogy is basically, Firefox is the browser for Linux, while Internet Explorer is the browser for Windows. Another example of embeddings being used in a different context is this baller2vec project that I worked on. And so this is what I presented at the MIT Sloan Sports Analytics Conference in 2018. And so the way this model worked is for each batter and for each at-bat in the data set, I took the batter's one-hot encoding and the pitcher's one-hot encoding for that particular at-bat, mapped them to an embedding, and then just concatenated those together and predicted the at-bat outcome. And so that could be like a home run or a single or a strikeout or something like that. And these embeddings ended up really capturing player talent quite well. And so, for example, in this case, we have a baseball player, Mike Trout, who's like a really amazing, he's just like really multifaceted and a really elite baseball player. If we subtract the average embedding for right-handed batters and then add the average embedding for left-handed batters, we get an embedding that's really close to the embedding for Bryce Harper, who is an equally, maybe not equally, but an extremely elite baseball player who's left-handed. And so Mike Trout is right-handed. His left-handed like counterpart, you might say, is Bryce Harper. And the model learned this just by learning to predict the outcomes of at-bats using these learned embeddings. So one other important concept for transformers is this notion of attention. And so the original motivation for these attention mechanisms are these sequence to sequence models, where they're often used in language translation, where basically you encode a input sequence that's in one language and you want to decode it into some translated language. And so when they were originally doing these tasks with recurrent neural networks, they would essentially, what they would do is pass the input sequence to a recurrent neural network and take that final hidden state and just use that final hidden state as input to a decoder recurrent neural network and try and decode the entire sequence. But this is like really hard essentially for these models to do, because you basically have to encode the entire meaning of that input sentence in just one feature vector for the model to be able to decode it. Attention basically allows the model to not have to memorize everything about the input and process different parts of the input when it's doing the decoding. And so the way it works is at a specific, so you pass your model, your input through the encoder, and then at each time step of the decoder, you take the decoder's hidden state, and then you take the hidden state for each of the inputs from the encoder. You concatenate so at this time step, for example, we would take the hidden state from the encoder for this word, concatenate it with the hidden state from the initial time step, or whatever time step we're at, of the decoder, pass that through an MLP, and get a score, a single scalar value. And then we do that for each time step of the encoder. So again, we're using the same hidden vector from the decoder. We're concatenating that with the hidden state from the encoder for each of these words, passing them through an MLP and getting a scalar score for each of these. You then pass that through a softmax, which gives you probabilities associated with each of the input hidden states that sum to 1. And then what you do is you take the convex combination, and so you just multiply the scalar times the encoder hidden state, and then add those up. And that basically allows the model to focus on different parts of the input sequence. And that's then combined with the decoder's hidden state and used to generate the next hidden state and make the prediction for that time step. And so what's really interesting is these attention mechanism kind of gives you a way to look inside of what the model is thinking. And so what you see in this figure here is an example of a model that was trained to translate sentences. So the input here is an English sentence, and it's trying to generate or decode the sentence in French here. And what you can see is that when it's decoding this part of the sentence, for example, the way English and French work, they basically reverse the order of the words for this particular group, the European Economic Area. And so you can see that when the decoder is at this portion of the translation, it pays attention to the words in the opposite order as you would expect it to do, given the way English and French behave. Okay, so that's attention. And so basically, if we combine this attention and embeddings together, we get a transformer. And so the motivation, again, is that recurrent neural networks are slow and cumbersome to train. And so the idea is that we can process sequences in parallel rather than sequentially using what's known as this, using this attention mechanism. And so probably the weirdest thing about transformers is that they, because they're not sequential by design, you have to somehow encode position in the inputs. Otherwise, the model would have no way to be able to tell which word, what the order of the words was. And so one way, and this is probably the weirdest thing about transformers to me, and one way they do this is by using a positional encoding. And so for your sequence of words in the input, to encode where they are in their position, to encode their order, basically, whether or not the words at the beginning or the end, they add these positional embeddings where for each time step, they learn a different embedding, and they just basically, so you have your word embedding, they basically just add a positional vector embedding to it and use that summed vector as the input to the transformer. And so this is really weird. I'll share these slides, but this is an answer on Reddit that of someone speculating why this might work. But it turns out that actually, if you have a causal attention mask, which I'll get into a little bit later, you don't even need these positional encodings, because the amount of information that is being processed at each time step increases, and that is its own positional signal, it turns out. But another way, the way you enforce this causal structure is by using an attention mask, where the mask tells you at which specific time step the model is allowed to look at, when processing a specific time step, what the model is allowed to look at or for the other time steps, essentially. And just down here, the takeaway is that these transformers are much more computationally efficient than recurrent neural networks, and they also don't have the same gradient exploding and vanishing problems because the path length is shorter.
Michael, we have a question in the chat. It says, is attention based on ONN, or they use different techniques?
So the attention, the way it works is it doesn't have to be a recurrent neural network. Basically, attention just means you have a query vector. And so it can be anything, but the way it was originally introduced was in this encoder decoder task. And so you can imagine we like have a recurrent neural network here, right? And then we get a vector for, we'll start at this time step. So we have our hidden state here. That's what is referred to as our query. And then we have key vectors that that are in a different set. So we have a query vector, and then we have a set of key vectors that we want to use to get scores. And so one way to do that is to just concatenate the query vector with all of these key vectors. So you have the number of keys is the number of inputs basically here. And then pass that through an MLP, and you get a score for each of the key vectors. And by passing that through a softmax, you get these probabilities that you can use to sum up so there's query, keys, and then value vectors. In this case, the values and the keys are the same, and that's usually the case, but they don't necessarily have to be. But then you use these scores, these attention scores or attention weights, to sum up your value vectors. And that once you sum it, you have that single combined input that you can combine with your other downstream task, essentially. So they don't have to be recurrent neural networks. So transformers are using attention without doing any recurrent neural network stuff. They are just basically at the first time step, it'll take this vector, and so it doesn't use an MLP. It takes the dot product. So it'll take this vector, and it'll take the dot product with all of the other input vectors, and those are the scores those are the attention scores for this particular input. And then takes a softmax over those, and those are then the attention weights for this particular input. And then you do the same thing for each input. So this one will take the dot product with all the other inputs. Those will be the scores. You take the softmax over that, and those are your weights. And then you combine the vectors. You take the weighted sum, and that's your attention input for that particular time step. Yeah, so I'll share these slides. I have a lot of links in here. I should have mentioned that, of really helpful resources that go into more details about how these techniques work. So yeah, if you're interested in digging into this stuff more, be sure to check out some of these links. Okay, so the standard transformer works by basically the input and output are individual words in the case of a language model, for example. So this is basically a special case of multi-entity sequences where the k is equal to 1. And so the way NLP transformers encode the temporal or the model the dependency between words in the input and the output is by using a self-attention mask matrix M that is the length of the sequence by the length of the sequence long. And what that basically does is that each cell in the matrix indicates whether or not the model can look at time step T2 when processing time step T1. And so, for example, if we look at the second row here, what this means is that when the model is processing the word at time step T2, it's allowed to look at both the word at time step T1 and the word at time step T2 when trying to predict the word for time step T3. And that just basically, it's the same pattern throughout this, where at each row, the model is basically allowed to look at all of the words that have occurred before it when trying to make the prediction for the current word. Okay, so to generalize the standard transformer to the multi-entity setting, we reimagined this self-attention mask matrix as a reshaped self-attention mask tensor, where each element of this 4D tensor indicates whether or not the model can look at agent PK2 at time step T2 when processing agent PK1 at time step T1. And so we can then reshape that into a matrix, which allows us to use the standard PyTorch transformer implementation without doing any additional work. And so what that looks like is what you can see here, where at each time step, the cell indicates whether or not the model can look at, when processing a specific player at a specific time step, that's what each row corresponds to. The cell indicates whether or not the model can look at a specific player at a specific time step. And that's what gives you this attention mask pattern that you see here. Importantly, this strategy is permutation, equivariant, or invariant, depending on the task, and which is exactly what we want because, again, the agents, so the players are unordered. And then the actual input to our transform then is going to be a TK by F matrix, where F is the dimension of our input feature vectors. Again, that's 512. And the way one way to include the positional encoding is use the same positional time embedding as to add the same positional time embedding to all the feature vectors at a specific time step. So all the feature vectors at time step T2 get the same positional, the same time embedding for time step T2 added to it. But it turns out you don't even need to do this because of this causal attention structure. And so actually my most recent version of this model does not even do this embedding step, because all you actually need is this attention mask strategy to encode position. Okay, and so one other challenge with this trajectory modeling problem is that the trajectories are inherently multimodal. And so what I mean by that is you could have like point guard, so you have a player who's at the top of the key, so like outside the 3-point line or something like that, and he has a defender right in front of him. So that player basically has two options, right? So like 50% of the time he might go to the left, 50% of the time he might go to the right. If we were to train this model using the standard regression framework, the model would just learn to predict that the player would go straight ahead because it would average basically the two outcomes. And we don't want to do that because that's obviously not representative of how the players actually behave. And so to capture this multimodal aspect, we bin the trajectories by overlaying a 2D grid over the trajectory space. And then basically we took the endpoint of the player's trajectory for that one step ahead trajectory and used that as the label. And then we treated the whole training procedure as a classification task, which allowed us to learn multimodal distributions of the trajectories because it assigns a probability to each bin as the output. And then all we did to train the model was use the standard negative log likelihood, where basically we just took the negative log probability of the player's trajectory, of each player's trajectory at each time step, and that was what we used for our loss. And then in the case of the ball, we have a 3D volume of trajectory bends because we have both the X, the Y, and the Z coordinates there. So what have other researchers tried before this? One common technique is to do a pre-processing roll alignment step where they use that 10-player input that I mentioned at the beginning, but they try to intelligently place players in specific slots by using this roll alignment strategy. What's interesting about this work is that when they add player identity as their input, so if they add player identity in addition to the player's coordinates as part of their input, the model actually does slightly worse. And so that's what you can see here. So when they don't include any identity at all, either team or player, this is the model's performance. But when they add player identity, the model actually does notably worse. And so that doesn't seem to really make sense because players have a wide range of skills, right? And so it seems like there's a lot of relevant information there when trying to predict what's going to be happening on the court. And so that doesn't seem like it's an optimal strategy. Another approach that people have done is these graph neural networks, where they essentially have a graph neural network that processes the players as the input. And so this is a more principled way than the roll alignment strategy because this model design is inherently permutation equivariant, like baller2vec, where what they basically did is at each time step, they use a graph neural network to process all of the player inputs, and then they into a recurrent neural network. And so the problem with this is that it's, again, using a recurrent neural network. And so we have those same computational efficiency issues that we were talking about before. But in addition, it's making assumptions about the relationships between different agents, because if you want to have different edge types between the players, you need to add, what they do is they add an edge type embedding as the input. And so this would be the node, the input vector for one player, for the player associated with I, the input vector for the player associated with J, and then they would have a relationship between them that would be captured in this type embedding for player I and J. And so this type embedding requires that you know something about the relationship between the players ahead of time to be able to choose the type embedding, right? And so this requires a lot more knowledge ahead of time than is required by baller2vec. And so, yeah, that's the way that model works. You guys can, I have some more resources here about graph neural networks and things like that if you guys are interested in learning more. Okay, additionally, most of these methods have been used like a variational approach where they are using basically variational methods that maximize the evidence lower bound instead of maximizing the likelihood or minimizing the negative log likelihood, depending on how you want to think about it. And this can lead to like really weird issues. And so I linked to a cross-validated post where people are talking about how they have to weight the two losses. So basically there's a KL divergence loss and then a likelihood component of the loss for these models. This is like fairly technical. And the KL divergence comes from these priors that you have to place over the latent variables. But basically, like I said, there's like these models can have like really weird issues, and they don't allow you to explicitly model the distribution of the trajectories as the output. You have to, it's this evidence lower bound, and so it's not precise essentially in that way. In our case, we're explicitly maximizing the likelihood of the data, and so when we get predictions, those are explicitly the likelihoods or the probabilities associated with the different trajectory outcomes. Lastly, some people have tried to use transformers for multi-agent setups, or not necessarily multi-agent, but multi-agent spatiotemporal modeling. So in this case, this Giuliari paper is using a transformer to model individual pedestrians. And so they didn't consider interactions at all. They only use individual pedestrians as inputs. And so it's basically exactly a language model. This other paper, you et al., use a combination of separate temporal and spatial transformers to model trajectories of interacting pedestrians. And so this is the architecture here, but basically they use 4 different transformers to process the inputs at separately, spatially and temporally, combine it, and then pass that through another transformer that does spatial processing, and then another one that does temporal. And so in our case, we're just using a single transformer to process all of the inputs simultaneously. And so we don't have to worry about these multiple components that can be kind of cumbersome to work with. Yeah, so other applications of transformer do you have a specific question in mind? So basically transformers can be used for any type of sequential data. So they had been originally used for language modeling, where you have like words are your input. They've also recently been applied to images, where you can think of a image as a sequence if you want, where each pixel has essentially, you can flatten your image so that the pixels are in order. And people have recently been using transformers for like image classification and things like that, and seeing how they compare to convolutional neural networks. And they've found that they work quite well, basically. So one paper I recommend looking into is Vision Transformers is the name of it, Vision Transformer. And so it seems like these transformers might end up being really useful for image processing as well. And so, yeah, and then like in my case, we're looking at multi-entity inputs. And so doing multi-agent spatiotemporal mining. So yeah, it seems like transformers, anywhere where you have a lot of inputs that have like a spatial or temporal structure to them, it seems like transformers are going to be like pretty useful. Okay, so how do we train our model? And so we used 569 games from the 2015 to 2016 season as our training set, and held out. There was an additional 32 testing games, 32 games that we used for testing. And so the training procedure was this online sampling regime, where we began by first sampling one of the games out of these 569. We then randomly sampled a starting time from that game timeline, and then use the following 4 seconds of data down sampled to 5 hertz from the original 25 hertz. Next, we randomly rotated the court to account for the fact that whether the team's going from the left to the right or from the right to left is completely arbitrary. And finally, we trained on that sample. And so this online training or online sampling regime gave us access to about 82 million different training sequences, which is 800 times more than prior work. So it's much more data than was being trained with prior work, used for training in prior work. And as a result, that allowed us to train a much larger model than had ever been trained in prior work. And so our model is basically almost identical to the original transformer. And so we had about 23 million parameters, which is about 80 times larger than the number of parameters used in prior work. And so what are the results? One way to measure the performance of these types of models is using what's known as the perplexity. And so intuitively, the perplexity is equivalent to the amount of uncertainty in a fair die with the same number of sides as your perplexity. And so if the perplexity of your model is 6, that means your model has the same amount of uncertainty on average as the amount of uncertainty when you roll a 6-sided die. In our case, baller2vec achieves a perplexity of 1.68 on the player trajectory forecasting task and a perplexity of 14.57 on the ball trajectory forecasting task. And so 1.68 is better than a coin flip. If we just use the training set distribution to make the predictions of the trajectories, we get a perplexity of 16.9 and 322 for the ball trajectory forecasting task. And so baller2vec is doing a really good job of compressing down this trajectory information. In addition, we compared baller2vec to a graph recurrent neural network baseline that had approximately the same number of parameters as baller2vec. And what we found is that not only is the graph recurrent neural network much slower to train, so it takes 4 times longer per epoch, which is exactly what we expect. But it also has 8.1% worse performance when given the same amount of training time as baller2vec. If we cheat and allow the graph recurrent neural network to train for twice as long as baller2vec, so this isn't like a fair comparison, because if we were going to give baller2vec more training time, we could make the model larger and things like that. But even when we give the graph recurrent neural network twice as much training time, it has 3.1% worse performance than baller2vec. if we probe baller2vec a little bit, we can see that it uses information about all players in the court through time, in addition to player identity, to model spatiotemporal dynamics. And so what we find is that we trained two different models, one with a single player as input and one with 10 players as input. And what we found is that the model trained with 10 players as input had 12.1% better performance. And so using more players gives the model more information and it works better. In addition, if we add player identity, we get another 3.8% boost in performance. And so interestingly, prior research either did not use player identity or found it did not help, like I mentioned with that role alignment pre-processing group before. And so we're the first to basically show that identity actually has useful information for this particular task. In addition, we compared the model's performance when only predicting the first frame of a sequence versus predicting the entire sequence. And what we found is that the model's performance on the entire sequence was 71% better than just looking at the first frame. And basically all this means is that baller2vec is using historical information to make its predictions, which is exactly what we want it to do. Interestingly, if we take a look at the player embeddings, a closer look at the player embeddings, we can see that these player embeddings encode individual attributes. And so what you see here is a 2D UMap of the learned player embeddings. And so a UMap is can kind of be thought of as like a nonlinear PCA. And what you see here is that the player embeddings cluster both according to their position and skill, where the points are shaded according to their block rate, a statistic in the 2015 to 2016 season. So you can already clearly see that these player embeddings are capturing some intuitive structure about the player's skills and physical attributes. If we take a look at the nearest neighbors of the embeddings, we can see that they actually are capturing fine grain qualities as well. And so the nearest neighbor for Russell Westbrook is like a 6'3" point guard, 6'3" point guard who's like really athletic and really explosive. His nearest neighbor in the embedding space is Derrick Rose, who is another about 6'3" point guard. So they play the same position, who's known for his athleticism. And so the embeddings here seem to capture fine grain qualities. Another funny one is that the nearest neighbor for Pau Gasol, who is a 7'1" center from Spain. So he plays like a European, a very like specific kind of basketball that's kind of distinct from American basketball, even though he's playing in the NBA. So he has this European style of basketball. His nearest neighbor is actually his younger brother, Marc Gasol, who's a 6'11" center, who obviously also plays a European style of basketball. And so again, these player embeddings are capturing like really fine grained qualities that intuitively make sense for the game of basketball. And then again, these features were inferred solely from learning to predict the ball's trajectory. So there's no additional information given to the model about these players' attributes other than just trying to predict where the ball goes at each time step. If we look at how the baller2vec's forecast trajectory forecast distributions varies because it doesn't have as much historical information and less certain when it basically comes to decision points, for example, when a defender gets close to it. And so what you can see in this sequence is on the left-hand side here, we have the ground truth trajectory at each time step. And then on the right-hand side, we have the predicted trajectory distribution by baller2vec. And at the beginning, you'll see that it's like basically really gray and kind of flat because the model is really uncertain. But as the sequence progresses, it becomes more certain until it basically reaches a decision point around here where it basically, you can imagine the player is either going to go right or straight and the model's not sure. And then it becomes more certain again as the player makes the decision. If we look at the, this is basically making the same point, but we can generate sequences. We can generate trajectories iteratively. And if we generate, so on the left-hand side here, you have the ground truth trajectories for a sequence. And on the right, we have generated trajectories given different amounts of historical information, of ground truth historical information. And what you can see is when the model has more historical information, the generated trajectories kind of look more natural and more accurate. But when the model has no historical information, it's kind of confusing what the generated trajectories aren't supernatural. Yeah, so someone asked about, can we apply this to football? I am collaborating with, I've had a lot of interest basically from the soccer or football community. And I'm hoping to basically be able to apply this to soccer. But yeah, the model design basically should, I would expect it to work basically out of the box, completely unchanged on soccer data, because they have very similar dynamics basically in how, I mean, it's not exactly the same obviously as basketball, but overall, you know, you have players interacting in complex ways and doing strategic things to try and score, and you have defenders against an offense and things like that. So yeah, I think that would be a really interesting data set to work with. Additionally, if we take a look at the attention heads in baller2vec, they appear to perform different basketball relevant functions. And so this is a common observation with transformers, is that the attention heads inside of them do sub functions that are relevant to the overall task. And so this particular attention head seems to recognize the ball handler's teammates. And so what we did, what you see here is a frame from 4 different sequences where the players are shaded according to the amount of attention given to the player by the model. And so players with more attention are lighter in color, and players with less attention, so closer to 0, are darker. And what you can see is that the squares in each one are much lighter than the triangles. And so this basically shows that this particular attention head is paying attention to the ball handler's teammates. This attention head is really neat, I think, but basically it regularly anticipates the recipient of passes. And so what you can see, again, the players are shaded according to the amount of attention given to the player by the model. What you can see is that the recipient of the pass lights up before the ball handler actually even initiates the pass. And so it recognizes that this guy gets open and anticipates the pass essentially. And so this isn't a cherry-picked example. This same attention head does this type of thing in many different sequences, which I found pretty interesting. Kind of fascinating, but there's concurrent work from researchers at Facebook, Berkeley, and NYU actually use a kind of similar conceptual design to try is a problem in bioinformatics where you have a bunch of sequences, for example, DNA or something like that, and you've aligned them in some way. And so like you have these sequences aren't completely identical, and so you first align them so that they seem to match as closely as possible. And in this case, you do like a type of language model, you apply like a language modeling type of thing to these sequences. And they basically considered their input as a set of sequences, and we considered our input as a sequence of sets, but they were doing this exact same thing, just described in different language. But basically their architecture is conceptually is very similar to baller2vec, but they use a sparse, they do a sparse operation with their attention mask. And funnily enough, I had actually implemented a identical sparse attention mask in baller2vec in my private repo that looks something like this. And so it's just kind of interesting concurrent work for completely different problems. Seems like a similar strategy. Importantly, baller2vec is actually still more generic though, because we are thinking of this attention mask as an attention mask tensor. And so we could encode, our model could handle like more complex relationships between the inputs, the entities at each input. And so you can imagine each input being a graph where nodes are connected in a sort of complex structure. Our model can inherently handle that because we're thinking of the attention mask as a reshaped attention mask tensor, and all you would have to do is basically encode that connectivity pattern in your attention mask. So that's the end. I have all the code for this project is available on my GitHub along with a link to the paper. I also have I ran a mini workshop when I was an intern at the Cleveland Indians, who are a Major League Baseball team in America, that basically introduced PyTorch to this group, PyTorch and deep learning to this group, or gave a workshop on PyTorch and deep learning to this group. And what I did is I implemented many of the standard deep learning components in pure NumPy, side by side with their PyTorch implementations, which gives you the opportunity to basically look at how these deep learning components work under the hood mathematically. And I've also reviewed a bunch of deep learning papers as part of my lab here at Auburn. And so if you're interested in checking those out, you can. But basically, that's the end. If anyone has any questions, I'm happy to answer them. And thank you again for the invitation.
Thank you so much, Michael, for this wonderful talk. Now it is your time, guys. If you have any questions and you want to ask it to Michael, feel free to leave it in the chat, or even raise your hand and we will unmute you so you can ask your question directly. We have a question in the chat. Based on what data the model give you a player some attention?
So this is, the attention is basically just derived from the internally. So all the input to the model is the player coordinates and identities. So for a specific sequence, if we go back to a sequence of input data is basically just a set at each time step that has where each feature vector, so we have a feature vector for each player, is the output of an MLP that takes as input the player's embedding. So we take the player's identity, map it to an embedding vector, his XY coordinates at that time step, and his the direction of his team's front court. And so the attention is just what the model learned to do basically internally when trying to learn to predict where the ball will go. I see another question about how did I collect this data? So this is a publicly available data set. I linked to it in my GitHub repo. But basically, yeah, the way this data is collected is there is a computer vision system set up where they identify the player and their coordinates at each time step. And so I'm not doing the computer vision part. I already have the process data of the player's coordinates and their identities. And yes, it's at each time step.
Great. I guess there are no more questions. So we definitely want to give a huge thank you to Michael. This was awesome and super interesting. Thank you again. And with that, thanks to everyone for joining.
Yeah, thanks a lot. Appreciate it.
Thanks, Michael.
Bye-bye. Thank you.
Oh,
Bye.
I just added the slides. Sorry, I forgot to add them at the beginning, but I just added the slides to the chat, and I'll send them to the group as well, so that they can be added along with the recording. Thanks again, everyone.
Okay. Thank you. Thank you again.
Thank you. Bye.